This is the third chapter in the electric power distribution course. This chapter covers the design considerations of primary systems. And this is the third lecture. This lecture will cover the basic design considerations for radial feeders with uniformly distributed load. Then, radial feeders with non-uniformly distributed load. And finally, the application of the ABCD general circuit constants to radial feeders design and analysis. Let's start with the analysis of basic design considerations of the radial feeder with uniformly distributed load. This figure shows a three-phase main feeder, having the same construction along its entire length L. Here, we mean by same construction, the same size of the feeder conductors, as well as the same spacing between the load tapping, along the entire length of the main feeder. Here, the line impedance is Z equals R plus JX, that is expressed in ohms per unit length. The load flow in the main feeder is assumed to be perfectly balanced, and uniformly distributed at all locations, along the main feeder length. Since the load is uniformly distributed along the main feeder, the load current in the main is therefore a function of the distance from the substation. Here, Di denotes the differential tapped off load current. Is is the sending end current at the feeder breaker. Ir is the receiving end current. Ix1 is the current in the main at points 1. Ix2 is the current in the main at points 2. L is total length of the feeder. X is the distance of the point 1 on the feeder from the beginning end of the feeder. And dx is the differential distance. Let's first understand what uniformly distributed main feeder means. If we denote the current at location X on the feeder with Ix, then the current at X equals 0 is Is, and the current at X equals L is 0. The decrease of the current Ix along the feeder is linear and can be expressed by this equation. Now, if we consider a small displacement dx on the feeder, the new current at location x plus dx is denoted by Ix plus dx, and is equal to Ix minus differential current di. Since the total load is uniformly distributed from x equals 0 to x equals L, then, we can write that di over dx equals constant k. Considering that di equals Ix2 minus Ix1, and dx equals x2 minus x1, then, we can write Ix2 equals Ix1 minus di. We can also write that Ix2 equals Ix1 minus di over dx times dx. That equals Ix1 minus k times dx. For x equals L, Ix2 equals Ir, which equals Is minus KL, and should equal 0. Because the current at the end of the feeder is 0. This implies that Is equals KL. And thus, K equals Is over L. Therefore, at any point x on the feeder, Ix equals Is minus Is over L times x. Or Ix equals 1 minus x over L, all multiplied by Is. So, we can express the differential voltage drop at distance x on the feeder as dV equals Ixz dx, that equals Is times 1 minus x over L times z and dx. The series voltage drop due to current Ix at any point x on the feeder can be expressed as the sum of differential voltages, or the integral from 0 to x of the previous expression of dV, which can be developed further and expressed by this equation, or by this equation. This final equation gives the voltage drop expression at any point x on the feeder, which is a function of x for given values of source current Is, feeder linear impedance Z, and feeder length L. Therefore, using the previous equation, and replacing x with L, it is possible to find the total voltage drop at receiving endpoint of the feeder, using this equation. Note that Z times L over 2, is actually equal to half the total impedance of the feeder. It is worth noting that, the distance x from the beginning of the main feeder, at which location the total load current Is may be concentrated or lumped for the purpose of calculating the total voltage drop, this distance is L over 2. Similarly, the differential power loss dPLS can be found using this equation. And the series copper losses due to current Ix, at any point x on the feeder can be expressed as follows. Therefore, the series copper losses due to current Ix, at any point x on the feeder is a third-order polynomial function of the distance x, for given sending end current Is, feeder resistance R, and feeder length L. Using this equation, and replacing x with L, it is possible to find the total copper loss per phase in the main feeder due to I2R losses as follows. Note that, the distance x from the beginning of the main feeder, at which location the total load current Is may be concentrated, that is, lumped for the purpose of calculating the total power losses, is L over 3. Let's consider a numerical example for the previous uniformly distributed load system. In this example, the length of the feeder is 100 meters. The feeder linear resistance is 1.6032 10 to the power minus 4 ohms per meter. The feeder linear reactance is 1.0516 10 to the power minus 5 ohms per meter. The sending end current Is is 100 amperes. And the receiving end current IR is 0. We would like to calculate and plot the accumulated voltage drop and power loss along the feeder. In this example, the current equation at any point x on the feeder, is given by this equation, which was determined previously. To solve such a problem, the following two equations in MATLAB and vary x from 0 to L can calculate the accumulated voltage drop and power loss along the feeder, using the previous equations, and just I am going to describe briefly the MATLAB script that is developed for this purpose. We first start by defining and initializing all given parameters. Next, we can use a for loop, in which we vary the distance x and calculate the voltage drop and power loss at each point x. Then we plot the results using the plot function in MATLAB. In our case, we plot the voltage drop along the feeder on one figure, and the power loss in a second figure. Here are the obtained plots of the voltage drop on the left-hand side, and the power loss on the right-hand side. Notice how the voltage drop and power loss change along the feeder saturate after a distance of 60 meters. This is because the current decreases when the distance increases, while the impedance increases. Next, we will study the case of radial feeders with non-uniformly distributed load. This single line diagram illustrates an example of a three-phase feeder main, which has the tapped-off load increasing linearly with the distance x, measured from the main power distribution substation. We assume that the current leaving the substation, at distance x equals 0, is Ix of 0 equals Is. And at the end of the feeder, at a distance L, the current is Ix of L equals IR, equals 0. Besides, the current variation over the distance is defined by dIx over dx equals k times Is times x. So, the current Ix, at any distance x on the feeder, can be determined by the integral from 0 to x of minus k Is x dx, which equals to, minus k over 2 Is x square, plus Is. Thus, the current IR equals Ix of L, which is the current at the end of the feeder at distance L, is equal to minus k over 2 Is L square plus Is, that should equal 0. Therefore, we can find that, k equals 2 over L square. And hence, Ix equals 1 minus x square over L square, all times Is. This is the general equation of the current, at any distance x on the feeder. Now, to calculate the voltage drop, at the end of the feeder, we need to first find the general equation of the series voltage drop on the feeder, at any distance x from the main substation. For that, we first express the differential series voltage drop dV, that occurs on a differential distance variation dx, as given by this equation, where dV equals Ix times Z times dx. Here, small z is the impedance of the feeder portion dx, or the linear impedance of the feeder. Replacing Ix by its previously determined expression, yields dV equals Is times 1 minus x square over L square, all times z and dx. Then, the series voltage drop, due to Ix current, at any point x on the feeder, is determined as the sum v dx, that is the integral from 0 to x of Is times 1 minus x square over L square, all times z and dx, which can be developed to obtain Is times z times x times 1 minus x square over 3 L square. Consequently, the total voltage drop at receiving endpoint is the sum of VDL, that equals Is times z times L times 1 minus L over 3, or Is times z times 2/3 of L. After calculating the voltage drop on the feeder, we can also calculate the power loss on the feeder, for the same non-uniformly distributed load. For that, we start by determining the differential power loss, that is, dPLS equals Ix square times Rn dx, which equals Is square times 1 minus x square over L square, all squared, and then multiplied by Rn dx. Note that, here R is the feeder resistance per unit length. After that, we can obtain the power loss at any distance x on the feeder, by calculating the integral from 0 to x of the previous expression of dPLS, which yields PLS of x equals RIS square, times the integral from 0 to x of 1 minus 2 times x square over L square, plus x power 4 over L power 4, all times dx. By expressing the integral of this polynomial function and developing it further, we can obtain the general equation of the power loss at any distance of the feeder as given by this equation, which is a function of x, x cubed, and x power 5. Therefore, the total copper loss per phase in the main feeder with length L, can be obtained by replacing x with L in the previous equation, which yields the following expression. So, the total copper loss, sum PLS, equals Is square R times 8L over 15. To summarize, we can recapitulate and say that, for a non-uniformly distributed load that has a current variation O this form, then, the series voltage drop, at the end of the feeder, is determined with this equation. And the total copper loss, is determined by this equation. Let's practice this case of non-uniformly distributed load, through a numerical example. So, we consider the same load distribution, as we have seen previously, for which, we know that the general expression of the current at any distance x is given by this equation. We consider the following parameters. The total length of the feeder is, L equals 100 meters. The linear resistance of the feeder is, R equals 1.6032 times 10 power minus 4 ohms per meter. The linear reactance of the feeder is, X equals 1.0516 times 10 power minus 5 ohms per meter. The current at the substation is, Is equal 100 amperes. And the current at the end of the feeder is, IR equal 0 amperes. Knowing all that, we are asked to plot the accumulated voltage drop, and power loss, along this feeder. To generate such plots, we can develop a small MATLAB script or program, that can calculate the accumulated voltage drop and power loss along the feeder, using the previously defined equations, which are presented below. This is a copy of the developed MATLAB script. When we write any script, we usually start by defining the objectives of the script, who developed it and when it was developed. Also, we add the name of the file where this MATLAB script is saved. Then, we start by defining and initializing the parameters which are given in the problem. Then, we need to develop the script that implements the previous two equations and calculate the accumulated voltage drop and power loss along the feeder, for different values of distance x. For that, we need to use a for loop, in which we vary x from 1 to 100 meters, which is the total length of the feeder. And we calculate the complex value of the accumulated voltage drop, using the given equation. Then, we calculate its absolute value. Then, we calculate the total copper loss, based on the given equation. Finally, we write the scripts for plotting the accumulated voltage drop in one figure and the power loss in a second figure. For that, we use the MATLAB function plot, and its related formatting options, such as displaying the grid, defining the X and Y labels and the title of the figure. After writing the full MATLAB script, we run it in the MATLAB command window, which generates the two plots, that are shown here. Notice how the accumulated voltage drop as well as the copper loss, vary sharply and almost linearly, for distances below 50 meters, but very less and saturate, for distances above 50 meters. This is expected, because, the fairer the distance, the smaller the load current distribution, which yields small voltage drop and power loss variations. Now, let's see the application of the ABCD general circuit constants, to radial feeders design and analysis. Let's assume a single-phase, or balanced three-phase transmission, or distribution circuit, characterized by the general circuit constants ABCD, as shown in the following figure. The mixed data that are assumed to be known, as commonly encountered in distribution system design, are source or sending end voltage, Vs, receiving end power, PR, and receiving end power factor, cosine theta R. What we usually need to find, are the receiving end voltage Vr, and sending voltage angle delta. Considering the receiving end voltage vector angle, as the phase reference. Using the two-port network theory, that you should have normally covered in circuits 2, we can write the relationship between, the sending end voltage and current vectors, and receiving end voltage and current vectors, as shown here. Where A, B, C and D are constants, which can be calculated as follows. A is determined as the ratio Vs over Vr, when IR equals 0. So, constant A, has no unit. B is determined as the ratio Vs over IR when Vr equals 0, so, constant B is equivalent to an impedance and its unit is ohms. C is determined as the ratio Is over Vr, when IR equals 0, so, constant C is equivalent to an admittance, and its unit is mho. Finally, D is determined as the ratio Is over IR, when Vr equals 0, so, constant D has no unit. Taking the phasor of Vr as a reference, we can draw the phasor diagram as follows. Note that, Vs is the sending end voltage phasor, which can be expressed as, a complex vector Vs equals absolute value of Vs, times, cosine delta plus j times sine delta. Vr is the receiving end voltage phasor. IR, is the receiving end current phasor, which can be expressed as, a complex vector IR, equals absolute value of IR, times, cosine theta R, minus j times, sine theta R. For a lagging power factor. Now, considering the two-port network equation, we can write, Vs equals AVR plus BIR, all expressed in phasor form, as complex vectors. where complex vector A equals A1 plus JA2, and B equals B1 plus JB2. Now, equating these two equations yields the following equation. This equation can be split into two, by equating the real parts from both sides, and also the imaginary parts from both sides of the equation. Now, squaring and summing the terms on both sides of the two equations, yields the following expression. Developing further this equation, can lead to the following one. Considering, PR equals, VR times IR, times cosine theta R, and QR equals, VR times IR, times sine theta R or equal PR tan theta R. We can develop the previous equation as follows. Now, taking a constant k hat as shown here, we can develop it further, as shown here. Note that, 1 plus tangent square theta r equals cosine square theta r, plus sine square theta r, over cosine square theta r, which is equal to, 1 over cosine square theta r, or sec square theta r. Thus, the previous equation can be rewritten as follows. We can develop this equation even further as follows. Notice that, this is a quadratic equation, which solutions can be obtained as shown below. Since we have two solutions, then the most practical one is usually considered. Here, the most practical one, means that the voltage, that is closest to the sending end voltage Vs, is to be considered. So, up to now, we were able to determine the magnitude of the receiving end voltage. Next, we have to determine the sending end phase angle delta. We know that IR equals PR over VR times cosine theta R, from which, we can deduce the expression of IR times cosine theta R, and replace it in the previous real and imaginary equation parts, yielding the following two equations. Finally, dividing the left-hand side equation by the right-hand side one, we can obtain the expression of tangent delta, as shown here. The obtained two equations are applied for a general distribution system. They can be used to determine the receiving end voltage magnitude and sending end voltage phase angle for any two-port network. Remember that, in this chapter, we are studying the design considerations, which are constrained by the voltage drop limit and power loss. So, knowing VR and delta, will allow us to calculate the voltage drop and the copper loss. The previous approach could be adapted to a simpler distribution system, consisting of a short primary voltage feeder, where the feeder capacitance is usually negligible, as shown in this figure. Here, we have two buses connected through one feeder with an impedance Z. The sending end voltage and current are denoted, Vs and Is respectively. And the receiving end voltage and current are denoted, VR and IR, respectively. For this case, using the two-port network theory of impedance and admittance matrices, we can relate the currents to the voltages and vice versa, using the impedance or admittance matrices. If we consider the admittance matrix, we can write the current and voltage relationship, as follows. Where, admittance matrix element, Y11 equals Is over Vs, when VR equals 0, that is equivalent to, Y11 equals 1 over impedance Z. Y12 equals Is over VR, when Vs equals 0, that is Y12 equals minus 1 over Z. Here, the minus sign is because of the actual direction of the current. Indeed, when Vs equals 0, and applying VR at the receiving end, the current flowing in the feeder, should be in the opposite direction of Is and IR. Y22 equals IR over VR, when Vs equals 0, that is Y22 equals minus 1 over Z. And Y21 equals IR over Vs, when Vs equals 0, that is Y21 equals 1 over Z. From the previous admittance matrix equation, we can write the expression of IS and IR as shown here. From these two equations, we can deduce the expression of Vs as a function of Vr and Ir as shown here. Now, using the ABCD constants, we can also write Vs equals AVR plus BIR. Then, combining these two equations of Vs, we can deduce the A and B constants, as a function of circuit impedance, as follows. It is clear that, complex constant A equals minus Y22 over Y21, that is minus the ratio of minus 1 over Z divided by 1 over Z. So, A equals 1. Thus, the real part A1 of complex constant A equals 1, and its imaginary part A2 equals 0. Similarly, we can notice that, the complex constant B equals 1 over Y21, that is 1 divided by 1 over Z. So, B equals feeder impedance Z. Thus, the real part B1 equals feeder resistance R, and the imaginary part B2 equals the feeder reactance X. Recall that, impedances, admittances and ABCD constants are all complex numbers, since we use phasor voltages and currents. After determining the constants A1, A2, B1, and B2, we can use the previously obtained equation of the receiving end equation, and replace these constants with their actual values in our example. This yields the following equation, which can be developed further. And further, to obtain this equation, in the bottom. In this equation, Z, PR, and cosine theta R, are all known, but K is still unknown, and needs to be calculated, in order to calculate the amplitude of the receiving end voltage VR. This is what we will do in the next slide. Indeed, considering the obtained values of the constants A1, A2, B1 and B2, we can also find K and tangent delta, using their respective equations that were previously defined. These yield the following equations for K and tangent delta. So now, we have all required equations to calculate the receiving end voltage VR and receiving voltage phase angle delta. Again, you should recall that, our objective is to calculate the voltage drop and the power loss in the feeder. That is why we need to know those two values. Let's apply what we have seen now to a practical example. In this example, we assume that the radial express feeder, shown below, is used on rural distribution, and is connected to a lump sum or concentrated load, at the receiving end. We also assume that, the feeder impedance is 0.1 plus J 0.1 per unit, the sending end voltage is 1 per unit, PR equals 1 per unit, is a constant power load, and the power factor at the receiving end is 0.8 lagging. Use the given data and the exact equations for K, PR, and tan delta, given previously, and A. Compute VR and delta, by using the exact equations, and find also the corresponding values of the IR and IS currents. B. Verify the numerical results, found in part A, by using those results in the equation, Vs equals VR plus, R plus Jx, times IR. To solve this problem, we start by answering question A, and calculate K, using this equation. Replacing all known parameters with their given values, we can obtain K equals 0.65 per unit. Now, in the equation of VR, we can replace K and all other known parameters with their actual values, and find the two mathematical solutions. Remember that we mentioned previously that, we need to choose the most practical solution and reject the other one. In this case, it is clear that 0.7731 per unit is more practical than 0.2287 per unit, which is too low and may result only, during faulty operation, and not during normal operation. Now, let's calculate tangent delta, using its equation. Replacing all known parameters with their actual values in this equations, yields a value of tan delta equal to 0.0323, which is equivalent to delta equals 1.853 degrees. On the other hand, the receiving end current is determined by this equation, which yields IR equals IS equals 1.617, with a lagging phase angle of minus 36.8 degrees. With this, we finished answering part A of the problem. In part B of the problem, we are asked to use the KVL equation to calculate the receiving voltage and compare it to the value obtained in part A. So using KVL, we know that VR can be expressed by this equation. It is clear that this value is the same as that obtained in part A. We can obtain the value of VR, that is equal to 0.773 per unit, and 0 phase angle. Of course, using the KVL is much easier and straightforward for this simple case. However, when the system becomes more complex, the KVL becomes difficult and the application of the ABCD general circuit constants becomes more justified. This is the end of this lecture. I hope that it was clear and informative. Thank you for watching.